Okay, in this lecture we're going to look at thin lenses, and there are two different types. There are converging lenses and diverging lenses. Now in this slide we see an example of a converging lens. And you can tell it's a converging lens because it's fatter in the middle here, it's wider in the middle than it is at the top and the bottom. And what that means is it's going to focus the light and bring it together and make the light converge. Now, just as we talked about with lenses, the rays of light coming from this candle are going to shoot off in every possible direction. And some of the directions are going to be away from the lens, some of them are going to be towards the lens. And the basic rule is the same as it was for mirrors. Parallel rays of light are going to converge at the focal point. And so if I pick the ray of light that's coming parallel to the optic axis, I know that it's going to go through the focal point. The same rule applies that the ray of light coming through the focal point is going to emerge on the opposite side. And it's going to come out parallel to the optic axis. So the first ray that we had was the parallel ray, and it went through the focal length on the other side. And by the way, that's something that's different between mirrors and lenses. A lens has two focal lengths, one on the left and one on the right. Now, if it's a thin lens, what we call a thin lens, the focal length on this side will be the same as the focal length on the other side. So it's the same value, just one on the left, one on the right. The third ray that we can draw is the ray that goes through the center. Now, if this were a mirror, we know that it would reflect at the same angle. But because it's a lens and the ray of light goes through the lens, it turns out it just goes straight through. So those are the three different rays that you can draw in your ray diagram. So here we have all three rays. The first ray is the ray that's parallel to the optic axis, and it goes through the focal length on the other side. This ray goes through the focal length on the same side, and it comes out parallel. And those are actually the two rays that I like to draw when I do the ray diagram. But you can pick whichever ones you want. The third possible ray is the one that goes straight through and it doesn't bend at all. And so where these rays intersect, we know that's going to be the image. And we can see that this is a real image because all three rays intersect there. All the rays of light go through that image. That means it's a real image. We can see that it's inverted, and it actually looks a bit bigger than the object, so it's been magnified. And we can actually calculate the distance where the image forms, and it turns out, and this is awesome, the equation for mirrors is the same equation for lenses. And so if we define the image distance and the object distance the same way, so the image distance would be the distance from the image to the lens, the object, that would be di, and the object distance would be the distance from the object to the lens, so that would be the object distance. This would be the image distance, the green one, and we can use that same equation that we used previously to calculate both the distance and the magnification. Let's look at an example. Let's consider an example with focal length being 10 centimeters and an object distance being 15 centimeters. Now, the equation that we're going to use is the very same equation, that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal distance. Solving for the image distance, we get the same expression that we got before. And now we can simply plug in our numbers. And so we get that 1 over the image distance is equal to 1 over the focal length, which is 10 centimeters, minus 1 over the object distance, which is 15 centimeters. And that's going to have a common denominator of 30. And so that's going to be 3 over 30 centimeters minus 2 over 30 centimeters, and that's equal to 1 over the image distance. and that's going to be 1 over 30. And when we solve that for the image distance, we get that the image distance is just going to be 30 centimeters. And that's where it will be located. And I can find the magnification doing the same thing. M is going to be minus di over do, and that's going to be minus 30 over the object distance, which is 15, and that tells me it's a minus 2. Okay, so here I have drawn my thin lens with the two 10 centimeter focal lengths, one on the left side, one on the right side, and my object at 15, so it's basically half the distance on the other side. And if I draw my two rays, the first ray that I want to draw is the one that's parallel to the axis, and it's going to come out and it's going to go through the focal length. And then the next ray that we're going to get is the one that goes through the focal length, and it's going to come out parallel. And where they intersect, that is going to be where the image forms. Now, if I look at my image, I can see that if we look at the math, we can see that the object distance was 15, the image distance is 30, so over here that's about twice as far over, so my ray diagram looks like it's supposed to. My image is about twice as tall. The minus sign here tells me that it's inverted. Also, the positive on the image distance tells me that the image is on the correct side. And what we mean by correct side, if this were a mirror, we would expect the light to come, reflect off the mirror, and go backwards and form an image over here. And so we would say that's the correct side. But for a lens, we expect the light to pass through the lens and form the image on the opposite side. So this is the correct side, and when the image forms on the correct side, it is said to be positive. So this positive 30 here, that's telling me that my image is going to be on the right side of the lens, which is coincidentally the correct side of the lens, compared to my object, which is on the left side of the lens. So the image forms on the opposite side. That's what we expect with the lens. If the image forms over on the left side, we would expect the image distance to be negative, and that would give us an indication of how our ray diagram should look. So you might ask yourself, how is it possible for an image to form on the wrong side with a thin lens? And the answer to that is if the object, in this case, this is the object here, if the object is inside the focal distance, so here is the focal distance, the object is closer to the lens than the focal distance is, and so we can follow our three rays. And so again, just like with mirrors, the ray that's on the line from the focal distance through to the tip of the candle, that line from there to there, the ray that continues that line to the lens, that ray is going to come out parallel. Rays that come along the line from the focal distance, rays along that line come out parallel. The next ray that we're going to draw is the ray that is parallel, and that goes through the focal distance on the other side. And then the last ray that we can draw is the one that goes straight through unencumbered. I don't really like to use that ray very much. I do sometimes, but a lot of people like that ray just because you don't have to remember anything. The one that goes through the middle just goes straight through. You don't have to draw all three. In fact, it's worse to draw all three. It's better to just pick two of them that you like, and draw those. Now the thing is, when we see these rays, again, these rays are not converging. They're not coming together. When the rays are spreading apart, if your eye is over here looking at these rays, your brain is going to interpret them as being projected backwards. And so these dashed lines here that you see, this ray that's coming out of the lens parallel, well, if your eye's over here, it's going to assume that that ray continues parallel to there. This ray coming like this, your brain is going to assume traveled in a straight line, and you can see that those two straight lines intersect there. In fact, all three of these backward projections intersect there. And so what kind of image would that be? that would actually be a virtual image. The rays of light aren't actually there. It's just where your brain thinks they are. And so if you were looking at through this lens on this side, you would not see this guy here. Instead, what you would see would be a magnified image behind where the object actually is. And so that's just sort of the optical illusion created by the geometry of the light. And coincidentally, that's how a magnifying glass works. So we just saw that if you want to create a virtual image with a converging lens, the way to do it is to put the object inside the focal distance. Let's look at an example. Let's consider a lens with, again, we're going to choose our focal distance to be 10 centimeters. And we're going to let our object distance be inside that, so let's say 5 centimeters. And so we can again draw our thin lens. So I've drawn my lens with the two focal distances. Each of those are at 10 centimeters. The object distance, DO, is going to be at 5 centimeters, so halfway between the focal distance and the lens. So something like that. And we can draw our rays. So here I've drawn the two rays that I like. The first ray is the one that is on the line from the focal point to the lens. And so I go from the focal point to the tip of the object. I continue that path until it gets to the lens, and I know that's the ray coming on the line through the focal point. That means it's going to come out parallel. The second ray that I like to draw is the one that's parallel, and I know that it's going to bend and come out the other side through the focal point on the other side. Now, of course, these rays are expanding. They're not converging. They're diverging. They're spreading apart. And so whenever you have that, you always want to project them backwards. And so I've drawn in those little dashed blue lines. So this ray is going to go backwards straight parallel. This one is going to continue on this line. And you can see they intersect right here, which coincidentally is at the focal distance. So we'll do the math and see if that works out. So again, solving our equation. In this case, we previously called it the mirror equation. Now we can call it the thin lens equation because that's what we're using it for. But it's exactly the same equation. Everything works exactly the same way. And so we can simply plug in our values. The focal length is 1 over 10 centimeters minus the object distance, which is 1 over 5 centimeters. If I get a common denominator of 10, that's going to be 1 over 10 minus 2 over 10, and that gives me minus 1 over 10 centimeters, and that is 1 over the image distance. So if I flip that, I get that my image distance, di, is equal to minus 10 centimeters. And again, the minus sign tells me that it is on the wrong side. So we expect that images for a thin lens to form on the opposite side to the object, but we can see this image has formed on the same side. It's on the wrong side, so that's why that minus sign is on that distance. If the distance is on the wrong side, the distance is negative in these formulas. We can also look at the magnification. We can say that m is equal to minus the image distance divided by the object distance. That's going to be minus 10 divided by 5 centimeters. And that gives us the minuses cancel, and we get that the magnification is 2. And the units cancel. And if we compare that with our ray diagram above, we see that the image forms in the right space. We see that it's bigger. It looks like it's about twice as big. It is upright, which we can see our magnification is actually positive. So that positive tells us that it is right side up, not upside down, which we see in our diagram. So the math works just the same. The rules work just the same. So if you can understand mirrors, you can understand lenses. They follow the same approach. The next kind of lens that we want to look at is what's called a diverging lens. And so with a diverging lens, we have the light does not come together, it diverges, it spreads out. And the way that you can tell that a lens is a diverging lens is that it's skinny in the middle and it's fat at the top and the bottom. So you can see that sort of shape. That's what creates the diverging path of the light. And the same rules apply as all these other ray diagrams. The application is just slightly different. So here we have the light ray that is parallel to the optic axis. Now if this were a converging lens, the one we just looked at, you would expect it to go towards the focal length on the opposite side. But instead, it diverges as if it were coming from the focal length on the same side. So this ray, the parallel ray, diverges from the focal length. So if I'm dealing with a converging lens, the parallel ray converges to the focal length on the right side. If I'm dealing with a diverging lens, the parallel ray diverges, it spreads apart from the focal length on the same side. Now this next ray is the one through the focal length, and we're not drawing the ray through the focal length on the left side. This is the ray that if it were to continue, if there were no lens in the middle, this ray would keep and go straight through the focal length. That ray would go straight through the focal length on the other side, and it comes out parallel to the optic axis. And I think that one's a little tricky to draw, so that's actually one of the cases where I don't draw that ray. I like the one that's much easier, the one that goes straight through the center. Because as with all of these lenses, we can see the one that goes straight through the center just goes straight through. And that one's just darned easy to draw. But if we put these all together, we can see all three of these rays. And so this ray, the parallel ray, diverges from the focal length here. The one that's going to the focal length on the other side comes out parallel. And the one through the center just goes straight. And where these light rays are diverging, so that means you project them back and see where they meet. They would meet right here, and that's where the image would be. And you can see there's only one ray of light that actually goes through the image, and since not all the rays of light go through the image, that means it's a virtual image. It's not a real image. And we can also see that it forms on the wrong side of the lens, again. Let's look and see how that works with an example. Okay, so for calculating where the image is, we're going to use that same equation, that 1 over the focal distance is 1 over the object distance plus 1 over the image distance. But there's one subtle difference that you just have to remember. With a diverging lens, the one that is skinny in the middle and fat at the ends, the focal length is negative. So when you plug in the focal length value for f, it's always going to be negative if you have this kind of a lens. Okay, so let's look at an example, and let's say that the focal length is 10 centimeters and the object distance is 15 centimeters. So I have drawn my object in, and I'm going to consider my two rays. The first ray that I like to draw is the parallel ray, and it diverges along the line from the focal length, and so that's going to come out like that. And then the next ray is the one that goes straight through the middle, and it doesn't diverge at all. And I can already see where those are going to cross right there. And that tells me where the image is going to form. And it's a little bitty there. I hope you can see that. But it's where those lines cross. And now we can do the calculation. So again, we have solving for the image distance, 1 over di equals 1 over f minus 1 over do. It's the same thing we've seen many times now. We can plug in the values, remembering that the concave lens, the diverging lens, is negative. That is, its focal length is negative. So I can plug in 1 over negative 10 centimeters minus 1 over the object distance, which is 15 centimeters. And I'll let you do the arithmetic. It's just get a common denominator and add like we've done it before. But when you do that, you get the image distance, di, is equal to minus 6 centimeters. And so you can see in our ray diagram above, the focal distance is at 10. That's at minus 6. That looks pretty good. We can also look at the magnification. We can see that that's a much smaller than the object. The image is much smaller than the object. So if I use the formula, the magnification is m is equal to minus di over do, and that's going to be minus, the image distance is minus 10, I'm sorry, minus 6, and the object distance is 15, and that gives us a magnification of positive 6 divided by 15. Now you could calculate a decimal for that if you want, but the key things that we can see here are that it's a fraction that's less than 1, so that tells us that the image is smaller than the object, and also it's positive. That again, for magnification, it means it's upright. If the distance is positive, it means the image is, or the object is on the correct side of the lens or the mirror. If it's negative, it means it's on the wrong side. If the magnification is positive, it means the image is upright. And that's what we see here. We see an upright image. We see magnification less than 1, which means the image is smaller. So our ray diagram and our math are in concert. And so what you're going to be doing in this exercise is you're going to be putting some objects at some different places and measuring where the image is, where the object is, and showing that indeed this equation does work. These equations do work.